Alright, today we're doing chapter 6, and the name of this chapter is Applications of Trigonometry, and one of the big things that we're going to do first is vectors. And vectors are rather important because they're used extensively in physics, engineering, and applied mathematics. One of the big things that they use them for is to plan airplane flight paths. If you ever sat and watched or have you ever seen anybody, air traffic controllers, there's this, one of those shows on Discovery, and they talked about air disasters, but they always show some traffic controllers, and they're sitting watching a screen, and what's on that screen are the flight paths of the airplanes, and they use those to show the direction and how far they're going using vectors. Let's go ahead and use in airplane flight paths. And so many times people are asking, when will I ever use this in the world? And there you go. This is one of those things that is applied is in the real world is vectors. And the other thing that we're going to do, one of the next sections, is parametric equations. And the thing about parametric equations is that they are used to simulate motion. Let me erase this. Simulate motion. And they use these equations in the analysis of motion in space. If you have things going, when you're on the moon or Mars, that's one of those things that they use for parametric equations. And then they use to represent points in the coordinate plane. Then another thing that they use is polar coordinates, and polar coordinates are used to represent like planetary motion. And what we're doing today, not today, but in this chapter, is convert rectangular coordinates, which we're so used to on just a flat, coordinate plane where you have an x and a y coordinate, and we're going to convert those to polar coordinates, and then we're going to convert polar coordinates to rectangular coordinates, and then also study the graphs of polar equations. So this is a big, thick, heavy, rich chapter, which applied stuff. You already know, you don't have to ask your teacher, when will I ever use this in my life? Well, there you go. This is one of those background pieces that you're going to use for lots of different things. If you're going in any kind of design or engineering or applied sciences, here we go. Okay, so one of the first things that we're going to do is learn about how to represent a vector. In the past in math, we've done things like dealing with numbers and something with temperature, height, area. That's represented by one number. If you have 24 square units of material, that tells you that's an area and how much area that's going to cover. Well, we're dealing today with vectors that have a magnitude and a direction. The big thing, what really magnitude means, is the length of something, and then you also have the direction which it's going. So a lot of times you're talking about some kind of flying object, and like I said earlier, is that if you think about a flight path of a plane, you want to see how far it has come and where it's going. So that's how that's represented, is by a vector. The big thing with vectors is the magnitude, and that is represented by these little symbols that have, let me see if I can write on here. Hold on. These little symbols. Why isn't this writing on here? Okay, I'm going to pause it. Okay, so where I left off is where the magnitude is represented by these little things right here, and magnitude represents the length or how far it's gone. So, and then we have to talk about where it starts from. So, again, what I was saying earlier is that we're going from a rectangular unit, which is pretty much this right here. This is a rectangular unit. We're so used to seeing a point on a coordinate plane AB. But now we're going to have to say that something starts where it's starting from and where it's going, and how long it took to get there. So a lot of times if it starts at this origin, that's where the tail of your arrow is, and then where it's going, or its direction, is represented by this arrow. And this is where it's ending up is AB. But this symbol right here is what they're talking about, the magnitude or component form of the vector. And then the magnitude of the vector is, I'll put this word magnitude, and that represents the length. And this is again in component form, and tells you how long it took you to get someplace. And then the direction again is from the arrow, which is going. Right. What's down here is this lovely text box, and I always tell everybody to highlight. I don't know if y'all realize that the reason these are put in boxes is because what's in here is some really important stuff, and it talks about a two-dimensional vector. Again, we're trying to take something that we're so used to seeing on a flat piece of paper, and it's rich in information. And if it's two-dimensional vector, it can be shown as the component form, which I explained a second ago. And that in the arrow, it was from the origin. I'll let you read it here. But the other thing, too, is the zero vector, and it has no length and no direction. That's just pretty much saying that it's sitting right here at the origin. So that's the only kind of important thing. If vectors also can start on different parts of the on a plane besides just the origin, if you think about it, again, I keep referring back to those planes. If you start on a different leg of a trip, and you start, say, from DFW, and you're going to DC, and you're flying northeast. So your home plane is your origin is DFW, and where you're going is northeast, and that's to DFW, and you're flying to DC. But say that you're not. That's just your stopover, and then you're going to go up to New York, or Newark, and you're going someplace else. So if you think about here, you're starting at DFW. That could be your origin. You're going here to DC, and then from DC you're going up north to Newark. And you can start here, and this is what I'm trying to explain is you're going someplace you can start in some other place besides the origin, and that's pretty much where we're going to go. And eventually we're going to talk about and figure out what's the total length of how far your plane has gone, or what's the ultimate direction, or where it ended up. And that's where we're headed today. But again, I just wanted to talk about that this little box was kind of rich in information. And the big thing, hopefully, is that you have one thing, is this little symbol talks about your magnitude and how far it's gone. Okay. All right, let's see if I can't get started on this. One of the big things that we're going to do today is how to represent a vector. One of the things in applications, it's easy to represent vectors with arrows that begin at one point, which is called your initial point, and your terminal point. And these vectors, it's kind of nice to, very rarely are you going to do it from where they start from the origin. These vectors start at one point other than the origin and end up someplace else. And we want to see if these two are equivalent, these vectors, these represented by these arrows RS. Okay, so I want to see if this arrow represented by RS is equivalent to the arrow of PQ. And how we do that is this head minus tail rule. And one of the things I want to see if these two arrows represent the same, or if they're equivalent, or they represent the same vectors. And how they are equivalent is two arrows with the same length and pointing in the same direction represent the same vector. So I want to see if this arrow RS is equivalent to the arrow PQ. And how I'm going to do that, again, is this head minus tail rule. And really I'm going to see this arrow, I have an object, and it starts here at R, and it ends up at S, negative 1, 6. I want to see what that vector is, and then see if it's equivalent to the arrow PQ. So one of the first things I'm going to do is I'm going to label my initial point as x1, y1, and my terminal point, or my final point, is x2, y2. So I want to see what that is. So I'm going to subtract my x2 minus your x1, and I'm going to have my y2 minus your y1. And see what that's going to simplify to. Negative 1 minus a negative 4 is going to be the same thing as negative 1 plus 4, which is going to be 3. And 6 minus 2 is 4. So this arrow RS represents the vector of 3, 4. Let's see what the arrow PQ is. I'm going to do the same rule. This time, this is my x1. This object starts at 2, negative 1. So that's my initial point, and my terminal point is at PQ. So that's my final spot, or my ending spot. So I'm going to subtract 5 minus a negative 1, and 3. I'm sorry, it's not 5 minus negative 1. Let's erase that. See, we all make mistakes. It is 5 minus... It's x. This is x2 minus x1. Definitely why I like to label my points. Alright, and then your y2, which is 3, minus a negative 1. Okay, this is going to simplify to 5 minus 2, which is 3. And 3 minus a negative 1 is 4. Okay, so these arrows RS and PQ represent the same vector. And the reason they represent the same vector is they have the same direction. And they go the same direction. And in the same length. Okay, now the next thing we're going to do is talking about magnitude. And magnitude talks about the distance between 2 points, or the length it travels. So, first thing here, if this looks familiar, is it looks like the distance formula. And that's exactly what I'm doing. I'm finding the distance between 2 points. But again, I'm talking about an object. This object started at P and ended at Q. So I want to find out what the length it traveled. If you remember, distance traveled is always going to be positive. And that's why we use absolute value signs up here in this equation. So again, it says I'm trying to figure out what the magnitude of this vector is. Going to use the distance formula. Again, because I've made lots of mistakes, I'm going to label my points x1, y1, and this is where I start, and then Q is where my terminal side. I'm going to have x2, y2. I'm going to find the distance traveled between those 2 points. Or in other words, I'm finding the magnitude of this vector, or the length of this vector. So let's see, my x2, negative 5, minus a negative 3. I'm going to square that whole thing, plus y2 minus 4, this was your y1 squared. See if I can do this one right. Okay, negative 5 minus negative 3 is going to be the same thing as negative 2. I'll square that, plus, this is negative 2, and I'll square that. Again, you're squaring both things inside here, so I'm going to be negative 2 squared. It means negative 2 times negative 2, which is 4. Negative 2 times negative 2 is 4. So the magnitude of this is 8. Now, the thing is, though, some of you, I got the length of this is the square root of 8. But I can reduce this as, some of us didn't spend very much time doing this in Algebra 2. I'm going to rewrite this. I'm just going to reduce this radical as the square root of 4 times 2. The square root of 4 times the square root of 2. The square root of 4 is 2. Okay. Depending on what you want, these two things are equivalent. This is just the simplified form. But the length of the vector PQ is 2 square roots of 2. So the distance is traveled. Again, the distance is always going to be positive. Okay, one of the things I wanted to just kind of clarify is that the magnitude of the vector represented by PQ, this is the magnitude of the vector PQ. Okay, the PQ is represented by the arrow, the vector is represented by the arrow PQ. It has the magnitude, which again is represented this way. This means absolute value vector. I mean, that's what this symbol means, magnitude. I'm just going to write here, magnitude is 2 root 2, which means that's the distance that it's traveled. Okay, one of the reasons I had to do the distance formula for that is because it was positioned someplace else other than the origin. But I want to look at this right here, which we didn't really talk about. Let's see if we can't find the magnitude of that. And it's represented, it doesn't have, I mean, it started at the origin, but what I can also show you is I want to, it's just the vector v. See, that's just represented with the letter. And it has this represented by, this is your A value and your B value. And I want to find what the magnitude of, of that is. So I'm going to do this. Again, in physics, I don't know, they might represent it this way. These two are equivalent. These notations are the same thing. But I'm going to find the magnitude of this vector v using a squared plus b squared. Okay. Again, when I plug something in, I spent a significant time in algebra talking about this. When I'm plugging my a value in, squaring it, I'm going to put in parentheses. Okay, so then my b value is negative 2. I'm going to square both of them. Guys, if you don't use parentheses and you plug in your calculator these two are not the same thing. This means the opposite of 2 squared. This means 2 squared. Okay, so negative 2 squared means negative 2 times negative 2, which is 4. And negative 2 plus negative 2 times negative 2, which is 4. Okay, I'm going to get the same answer. But guys, so these two arrows represent the same vector. They have the same direction and same magnitude. But I just wanted to show you this is called, this arrow right here is position arrow because it starts at the origin. Alright, now we're going to do some, I guess, basic algebra of vectors. One of the big things here is I want to kind of re-emphasize what a position vector is and what's not. I'm sorry, yeah, or standard position, and that is if it's standard position is a vector that starts at the origin. Let me kind of right here. These two are this vector u starts at the origin and ends up here, and vector v starts at the origin and ends up here. What those are called standard representations, standard positions of vectors. If you're adding two vectors, if one of them starts at the standard position, it starts at the origin, and like on this one is u is standard, it starts at origin, ends up here, and then I'm going to add the vector v that doesn't start at the origin and ends up here. This is if I'm going to add those, they call this vector the resultant. Resultant means the final piece. What if I add vector u and vector v together? I'm going to use this right here. I guess I can highlight this. This one. Okay, if I'm going to add two vectors together. Now, if I'm looking at this, I'm going to use this. This represents two standard positions of vectors u and v. They both against her. The origin, I'm going to use this parallelogram representation. That still going to use the same rules. Same rules apply, but it's just kind of confusing why you would use different methods to add two vectors together. Again, this just depends on where they are and where they start and where they end up. One of the other big things I need you to realize is, this is another vocabulary piece, is the scalar. Scalars are constants. They're numbers. Just like you're multiplying, you have something 3 times as big or 4 times as big. 3 is your constant, but really, scalars is just a synonym for a constant. Scalars are just your numbers. And what they're going to do is they're going to increase or decrease vectors by certain, depending on different things. They can change the length or the direction. And that's one of those, I guess, vocabulary things. When you start seeing it, scalar is just a number. It's a constant that we used in algebra. Alright, so again, let's start doing some algebra. It wants us to do some operations on these vectors. Again, I guess depends on what's given and what they want us to do. And the first example 3 in letter A, they want us to add vector A and not vector A. In letter A, they want us to add vector U, which again, it starts at the origin and ends up, its terminal position is -1, 3, and it wants us to add vector V to it, which starts at -1, 3, and ends up at 3, 10. We're going to use this vector operation, and again, what we were doing before, we were representing a vector with an arrow. They use this vector, this bold U. This is another way of calling this vector. It's just a different representation, but it's called vector U, and then this is vector V. You just pay attention to the slight that U was bolded and V is bolded, so it's asking you to call it this vector U and this vector V. So I'm going to add those two things together, those vectors, and I'm going to use this vector addition property, and let's see, I'm going to write the property here so you can see it. If I'm adding those two together, it's going to be U1 plus V1, and then U2 plus V2. Okay, and this is the resultant vector. I always just label mine too. This is U1. This -1 is U1, and this is U2, and then this is V1 and V2. We always get really confused. These are vectors with they're not ordered pairs, so just FYI. But I'm going to add U1, which is -1, and add it to V1, which is 4. And then I'm going to have U2, which is 3, and I'm going to add it to V2, which is 7. Alright, so these together is 3, 10. So my resultant vector is 3, 10. That was pretty easy. But one of the things, too, I want to kind of talk about is this. And 3 is your scalar. And your scalar K, or a constant, or what we call this, the number. But it represents, what I'm doing this is I'm going to, this is your scale, your K, or your scalar. And it represents your stretch or your shrink. So it's kind of, when we were doing stretching and shrinks with functions, it's kind of what we're going to do here. I'm going to take this U, this one of these, and I'm going to make it 3 times as big. So how I'm going to do that, the operation up there, I'm going to move it down a little bit so I can see it. I'm going to take this, B, and the operation is 3, and I'm going to, this is a bold U, so I'm taking it, my vector U, and I'm making it 3 times bigger. So it's kind of like My vector u is -1, 3. And I'm going to multiply 3 times each one of those units. So it's going to be 3 times -1 is -3. And 3 times 3 is 9. So I'm just showing this is exactly what's going on here, where that if I take u and I multiply it times 3, it's a vertical, or it's a stretch of 3. It's making it 3 times longer by a factor of 3. Okay, again, this one, guys, because k was, or your 3 is positive, it's going in the same direction. So it's making it 3 times longer, and it's still going in the same direction. If you have a k that's negative, it's going to make it, it's going to stretch it or something, but if it's negative, it's going to change its direction. It's going to make it go in the opposite direction. Okay, now the next thing in C is I'm also going to, there's 2 things I'm going to do for C. I'm going to take my vector u, make it 2 times bigger, and add it to vector v, but it's going to change the direction of vector v. So I just I'm going to move this over and show you the math on that one. So the first thing I'm going to do is oh, that's kind of fun. I'm going to reorientate that, make that a little bit better. Definitely technology is a fun thing. Do it like this. Hit the pen. Okay. So I'm going to take, make sure I'm doing this, 2, and I'm going to multiply it times my vector u. Vector u up there on the page, it said it was -1, 3. And I'm going to add it to vector u, but before I do anything to vector v, I'm going to change its direction. Okay, so as in any algebra, I'm going to do my orders operation. So I'm going to make vector u bigger, 2 times bigger. So I'm going to have -2, 6, and I'm going to add it to vector v that I've changed the direction. And it's going to have the term 4, -7. -4, -7. Okay, so now I'm going to add these 2 together. So again, to add them together, I have to have, this is, I'm going to erase this. This is my u, and this is v. And a lot of times they bold them, because that's how they represent them. Okay, and this is u1, u2, because that's what 2, 6 is, plus v1, v2. Okay, so I've done changed them, and now I'm going to have a resultant vector. So I'm going to have to use that property of u1 plus v1. Okay. And then I'm going to have u2 plus v2. So how I'm going to add those 2 things together, those 2 vectors together. So u1 is -2 plus -4. And then, so I have to label them. Let's see, u2 is 6 plus -7. Alright, my resultant is going to be, this is -6, -1.